Welcome to our second lecture, 3.2, Graphs of Functions. Again, this is Professor Bailey from Brookhaven campus at Dallas College. We're going to continue to look at graphs of functions. Remember that we looked at functional notation in the last section. Functional notation uses this f of x or a letter of x. Typically, the first letter, the f in this case, would denote what the function is about. For example, if we were looking at a cost function, it would likely be c of x as opposed to f of x. So when we're graphing a function, remember we're using the Cartesian system, which is the x and y axis, and it's important for us to remember that f of x is just another name for y. So if we're going to graph a function f of x, this is the same as graphing the equation y equals whatever that f of x equals, okay? It consists of all the points, x, and f of x, that is every point whose first coordinate is an input number from the domain, and whose second coordinate is the corresponding output number. All this is saying is that a graph includes all points that are part of the solution, the x and y value, that are actually on the line or the graph. In this case, it's just a straight line. So for example, in the graph that you see here of g of x equals 0.5x minus 3, when x equals 6, y equals 0. So this point, 6, 0, is actually on the graph, so it is part of the solution. Where if we looked at the point x equals 2 and y equals 0, this is not a point on the graph. It is not a solution to this function. When we have a function whose graph is a straight line, we call that a linear function, and you can see the word line right in the title. The rule of a linear function can always be put into f of x equals ax plus b for some constants a and b. And what we're going to find out later, a actually represents the slope of this line, and b represents the y-intersect, or where the line or the function, in this case the line, crosses the y-axis. So if we graph these equations, now notice that, again, here's a better example, all right? If we put in x equals 3, we're going to use the first equation. 3 minus 2 is 1, and we can see that point right there at 3, 1, okay? If we look at another value less than or equal to 3, if we look at x equals 0, we get 0 minus 2, or negative 2, and you can see that point on the graph at 0, negative 2, going downward from right to left. In the second equation, we're going to use values greater than 3, but it is important for us to also put in the boundary value as well. If we plug in 3, we get negative 3 plus 8, which equals 5, okay? Which is here, this very first point on the second graph. Notice it is an open circle. Open circles indicate that this point is not included. Or if we look at down below at 3, 1, we can see they're closed circles. It is part of the graph. It is very important that you graph the equation that does not include the boundary, but to use the boundary values and use an open circle. And then you can see the rest of the graphs here. So I'm going to just show you some common graphs. These are in your textbook as well, and you should know these general shapes. Absolute value, you'll see it in the description, f of x equals the absolute value of x, is just the non-negative value of whatever the function is inside. In this case, it's just x. Absolute value is a measure of distance, and distance we always measure in positive numbers or 0. And so that's why absolute value is there, because often in terms of travel or movement, we use positive and negatives to indicate direction as opposed to the actual distance we travel, okay? So we can see here that when x is negative, for example, negative 1, y is positive 1. When x is negative 2, y is positive 2, etc. Notice that on the right side of the y-axis, the value of x and y are the same, because the absolute value of a positive number is just that same positive number. The identity function, this is y equals x, okay? They're just the same thing, and this is just a diagonal. So when x is 0, y is 0, x is 1, y is 1. When x is -3, y is -3. Quadratic functions are when the largest power on the variable is squared. So this might be f of x equals x squared. F of x equals x squared. A cubic function is when the largest power on the variable x is, or any variable, is a 3. So the graph you're seeing here is x cubed. Y equals x cubed. Here we have a, a root equation. Remember, we cannot take an even root, a square root, a fourth root of a negative number. So this starts at 0 and increases to the right. This is the y equals the square root of -x. So how do we graph functions? Linear functions are pretty straightforward. But the first thing we want to do, as we did in the last section, is think about the domain of the function. And really this question is asking you, are there any values of x, the domain, remember the domain is input, are there any values of x that are not allowed based upon the equation or function? We had two cases, remember? If we had a fraction, a function that was a fraction with a variable in the denominator, we would set that denominator equal to 0 and find the values of x that are not allowed. Because remember, you cannot divide by 0. 0 cannot be in the denominator. What I always say to students is 0 is your friend, don't lock him in the basement. So what we're trying to find is values that of x that are not allowed, because then they're going to have they're not going to have a point at that value of x when we graph it. It's going to either have a hole or an asymptote. Okay, the other type of function, so we first looked at fractions. The other one was even-rooted radicals, the square root, the fourth root, the sixth root. Remember, we can only take even roots if the x value is 0 or positive. So all of these would start at 0 or potentially, whatever's inside the radical, inside the house. For example, if we had the square root of x minus 2, then x minus 2 cannot be equal, x minus 2 has to be greater than or equal to 0. So once we figured out what numbers of x are not allowed when we do the domain, then we use other numbers that are allowed and start finding the y values and building that table so that we can start plotting points. And that's what the rest of this is saying. So find out if there's any x that's not allowed, that's the domain, then pick some x values, find the y values, etc. In this course, you actually have a calculator that you can put in the function, and you should be able to see it pretty clearly. But it's a good idea to know, especially at this basic level of graphing, what your calculator is actually doing. Okay. One of the easy ways, or maybe helpful ways to graph a function is to use intercepts. Remember, the x-intercept here in green is when the graph crosses the x-axis. Remember that an x-intercept always has a y value of 0, because everywhere along the x-axis, the y value is 0. And by corollary, the y-intercept is where the function crosses the y-axis, and the x value for a y-intercept is always 0, because the x value on the y-axis is always equal to 0. So if we're looking at a formula or function, y equals 2x minus 2 in this example here, we can find the x and y intercepts by putting the other variable equal to 0. So if we want to find the x-intercept, we set y equals 0 in the equation and then solve for x. Okay, x equals 1 is not the x-intercept. The x-intercept is a point, and so you have to label it as such. X equals 1, where the graph crosses the x-axis. But the x-intercept is a point, comma, 1, comma, 0. I'm sorry, parenthesis 1, comma, 0, parenthesis. To find the y-intercept, we are going to set x equal to 0. So we get y equals 2 times 0 minus 2. And we get y equals negative 2. Again, y equals negative 2 is not the y-intercept. Parentheses 0, comma, negative 2. The ordered pair, the point, is the y-intercept. If you put y equals negative 2 on a test for the y-intercept, you will get it wrong. The correct answer is parentheses 0, comma, negative 2 parentheses. These are often easy to see visually. Here we have an x-intercept at 2, 0, where it's crossing the x-axis. We also have another an x-intercept at negative 4, 0. We also have a y-intercept at 0, 3. When you're doing graphs and also points, make sure that you put them in the correct XY order. It's very easy to place those. Okay, since we had such a little bit of a problem here, or this is a challenging area, these piecewise, I wanted to go ahead and do another graph of these. So the first thing we're going to do is look and see if either of these functions are not, we're going to check their domain and see if there are any values not allowed. X squared, that's not a fraction. The first function is not a fraction. It's also not a square root or an even root. So this is allowable for all values of x. So the first function has no problem. The second function, however, is a square root. And remember what's inside here, specifically x minus 1, must be greater than or equal to 0. The square root of 0 is 0. The square root of positive numbers we can get. But the square root of, for example, negative 2, we cannot find that. So we first have to figure out what value of x is not allowed by setting x minus 1 greater than or equal to 0. First, we've gone ahead and picked some x values to go ahead and find the graph for x squared, the first function. And here we go all the way up to 2, because that's our boundary. Remember, with these piecewise, we start on the right. We want to do values less than or equal to x for this first function, but they go up to 2. For the second function, we're going to start at 2 and go to the right. Okay? And again, when we graph the second function at 2, we are going to use an open circle. Okay? If we make x minus 1 greater than or equal to 0, to find the domain, we will get x minus 1 greater than or equal to 0. When we add 1 to both sides, we get x is greater than or equal to 1. Okay? But notice this problem, this piecewise function, already defines that this function is only valid when x is greater than 2. So we don't have any points that don't exist based on the definition. And because of this, the domain has to be greater than or equal to 1, but we've defined the problem that we only use this formula when x is greater than or equal to 2. So we won't have any holes in the graph. Now we just plot these points. And again, the important thing to do here is to remember that at x equals 2, we use the first equation. So we have these points that you can see plotted, and specifically at 2, we've enclosed or circled in or filled in, the dot for the first equation. The second equation is 2, 1. Notice this is an open circle, which means this does not include this point because this is only for x is greater than 2. You must include this value at 2 with the open circle. If you don't include it and you start at 3, you're going to get this problem wrong. Okay? So this is a simple exercise in how do we read a graph and how do we find values. Okay? It's telling us to find the functional values f of 1988. Remember, f of x, f of anything is the y value. So what this question A is asking is, what is the y value in 1988? most of us are pretty familiar with charts. So we go to 1988. We can see these lines are the odd years. So 1988 is going to be between 87 and 89. We go up to where the graph is, and we can see there's a dot there, and the mortgage rate is at 10%. This is a real graph, and it's so the mortgage rate, a 30-year fixed-year mortgage in 1988 was at 10%. Okay. We do the same thing with 2009. We're going to go across the graph until we hit 2009, because f of 2009, it says what is the y value when x is 2009. So we go along the x-axis to 2009, then go up to the graph or down to the graph. In this case, it's up, and then look at the y value. What is the y value? We take this y value across, and we see that it's 5%. Okay. So f of 2009 equals 5 because this point is on the graph. Okay. So average mortgage rates were 10% in 1988 and 5% in 2009. It is very important, if you're answering a specific question, not what is the functional value. F of 1988 is 10. But if we asked you what was the average mortgage rate in 1988, it's not 10, it's 10%. So you need to pay attention to whatever these units are for y and the units for x. The x is a year. Okay. So now it says during what period were mortgage rates at or above 7%? Now the rate is the y-axis. So we're going to go to 7. Where's 7 on our graph? Y equals 7. The average mortgage rate was 7 or above. We're going to go across and see where it's above. Well, we can see it's either a little above or equal to 7 in 1993. It continues over to 1998, but it doesn't go below. It hits the line and continues on. So we actually have a range here from 1993 all the way to 2001. So for B, we're just looking at the graph. We found where the y value is 7 or above, and even though it comes down and hits 7, it goes back up and then hits 7 again. So we're going to use that whole range from 1980. Wait, did I do something wrong here? 7, that's not right. 1985, I've got 1993 to 2001. Oh. Look at that. I made my own mistake, so I'm glad I did that. Here I went to 7 and started here where it was equal to. But of course, everything from the very beginning of the graph is above 7. You see how easy it is when you're looking at graphs, and I've looked at this graph. I've used this for years. It's real easy when there's something that I know to make a simple mistake. That was not planned, but that's a great mistake for me to make, hopefully for you to pay attention to the details here. So when is it above 7? Well, of course, it's above 7 from the very beginning. It's a little confusing in 1993, but it's either on or above the line. It's a little confusing in 1998 because it's actually on the line 7, but it still stays at or above until 2001. So from 1985 to 2001, the mortgage rates were above or at 7%. We can do the same thing now with when they were at or below 5. We're going to go to the mortgage rates are a y value, so we're going to go to 5 on the y value axis and see where it first hits 5 and where it's below. And we can see that's from 2009 to 2011. All right, just a quick reminder again. Remember that the vertical line test tells us if a function, when we can look at a graph and see if a function is if an equation or a graph is for a function or not. If a vertical line goes through the graph and only touches at one point, like in the graph in A, no matter where I draw a vertical line, an up and down line, I'm only going to touch that graph at one point. So A is a function. Notice in B, we can see automatically that the y-axis is going through at more than one point, so B is not a function. A vertical line only touches a function at one point and one point only. If it touches more than once, it is not a function like in B. In C, it's a little bit confusing because it looks like these lines are getting straighter, but they are slowly getting wider. So technically, it's still not touching at any more than 1 point, and so C is the graph of a function as well. The checks are indicating these are functions. This ends our lecture for 3.2. Please reach out, try your homework, and let me know if you need any additional assistance.